Now, in here right now, we have Richard Steenbergen, who is walking up here, who's going to talk to us about, is going to give us a whole brand new and improved version of everything you always want to know about optical networking, but we're afraid to ask.
And if you're not afraid yet, you will be. Yep. Alrighty. So you can see by the slide that this says updated June 6th because I managed to slip in some last minute changes as per usual at the last second. That's why the PC loves me. So this talk is everything you always wanted to know about optical networking, and if you've ever done any of my previous ones, you'll know that this one is fairly revised. I've probably changed out about 30–40% of the content. I tried to modernize it. I tried to really get into a lot more depth in some areas, so hopefully there's some new content that no one's ever seen at a NANOG before. So the purpose of this tutorial, why am I here talking about optical networking at a NANOG? The internet industry is largely based around fiber, but there's a lot of people out there that just work with it at a packet level, at a router level, that really don't have any real technical understanding of what's happening inside that fiber. So that leads to a lot of errors, misconceptions, all kinds of confusion and problems. So really the purpose of this presentation, it's not going to make you an optical engineer, or if you feel like it did, just remember I left out all the math, and optical is a field full of math. So really it's just to kind of help educate everyone about all the different pieces that are involved in running an optical system, from the mundane to the advanced and the unusual. Well, hopefully it's interesting. So I'm going to start with the very basics of fiber optic transmission. So ultimately, fiber is nothing more than a waveguide for light. So all that means is light goes in one end and comes out the other. So it's commonly made of glass or silica, but it can also be plastic. But why do we use fiber in the first place? Well, it's really low cost in terms of other materials. So even compared to copper, it's very low cost. Glass is cheap. It's very light. It's pretty flexible. It carries a tremendous amount of information. So today we have 20 terabit systems all over the place, and that's only going up from there. You can easily carry lots of independent signals with it. So you can do things where you can add capacity over time, you can add channels over time, you can add customers over time, they don't interfere with each other. It lets you carry these signals for thousands, tens of thousands of kilometers without having to regenerate. And ultimately technology keeps getting better and better, so we have lots of fiber in the ground that was put there in the 80s and 90s that was designed for 100 meg services that today is carrying terabits. So fortunately, the technology of the glass doesn't really change. We just get better and better with what we put on it. So a quick flashback to high school physics. When light propagates through something, through a vacuum, it's theoretically the fastest thing that can happen in the known universe, right? So that speed is what's called c, and it's roughly 300 million meters per second. So for shorthand math, you just call it 300,000 kilometers per second. When light passes through a material that's not a perfect vacuum, it propagates slower. So the speed that the light propagates relative to that vacuum is what's called the refractive index. So for example, water has a refractive index of 1.33. So that means when light propagates through water, it's 1.33 times slower than if it was propagating through a vacuum. So what happens when light tries to pass from one medium to another with a different index of refraction is that you get a reflection instead. So if you've ever looked underwater, you've looked up and you've seen a reflection down, that's what you're seeing. So it works like this. It's a principle called total internal reflection. So inside your fiber, you actually have two different types of glass. You have a core and a cladding, and they have different refractive indexes. So what happens is when the light comes in and it tries to go outside of the core, when it tries to leave the core, hit the cladding, the different index of refraction causes it to be reflected back. That's what keeps the light inside the fiber and keeps it propagating down instead of leaking out the sides. And that happens as long as it comes in within a certain, what's called an acceptance cone. So there's angles of light that can come in, and as long as it hits at just that right angle, then it will continue to propagate forever. So here's a demonstration from Wikipedia using a laser pointer and a little piece of acrylic, and you can kind of see the behavior. So what do we actually do with the fiber? Well, remember the vast majority of fiber that's out there is duplex systems, right? So we have fiber pairs. We run two strands of fiber, and one is used to transmit one direction, one's to transmit the other direction. So transmit, receive, depending on which side you're looking at. And it's not that that's the only configuration. There's plenty of ways to do things with single strand fiber, but this is kind of the cheapest, easiest way if you just have the simplest components. And so this kind of holds true whenever fiber is really cheap. But like I said, it's perfectly capable of doing more complex complex things. It's just a cost-benefit trade-off as to how much you're willing to do that. So the most basic distinction you can have when you talk about fiber is what's called multi-mode versus single mode. So multi-mode fiber is specifically designed to be used with these cheap light sources. So what's happening here is you've got an extremely wide core. And the reason that you want that is it lets you use these cheaper, less precisely focused, aimed at calibrated lasers or LEDs or whatever light source. The downside of this is that it comes at the expense of reach. So you aren't able to get long distances with it, but you're able to work with these cheaper optics. But yeah, modal dispersion is the name of the thing that limits your reach here, and I'll talk more about that in a second. So there's a couple different types of multimode. There's OM1 and OM2, so these are your common orange fiber jackets that you're going to see when you're walking around a data center. These are kind of known as FDDI gray. This was originally fiber that was designed for 100 meg FDDI services. So there's two versions, one with a 62.5 micron core, one with a 50, and they're very similar. They're designed for originally 100 meg, 1310 nanometer signals, and it really starts to fall apart when you try to do 10 gig, right? It becomes not scalable, not tenable. So then we came up with another type of fiber called OM3 and OM4, so there's different versions of it. And this is what's called laser optimized fiber. And these are your aqua, so your light blue colored jackets. So these fibers are specifically designed to work with these 850 nanometer short reach lasers. They much more easily support speeds like 10 gig. So instead of doing only 26 meters on an OM1, you can go 300 to 500 meters with a 10 gig signal now. And it's pretty much required for a 40 or 100 gig signal, which is actually 10 and 25 when you get into the insides of it. So you see this more and more in modern high-speed networking. But remember, multi-mode fiber itself isn't actually cheaper. Multi-mode fiber is more expensive than single-mode fiber. So the reason you use it isn't to save money on the fiber, it's to save money on the transceivers. It lets you use these cheaper transceivers. So single mode fiber is the other kind, and that's really what you use for all your high bandwidth and all your long distance stuff. So it has a much smaller core. It's going to be between 8 to 10 microns in size, and it has no inherent distance limitations caused by the modal dispersions that limit you with multimode. So typically you see distances of about 80 kilometers. That's kind of the standard magic number between sites without amplification. And with amplification, you can transmit a signal thousands or tens of thousands of kilometers and still get it through without having to regenerate. But single mode fiber has a massive array of fiber types. So it also has something very similar to that OM1, OM2. It's called OS1 and OS2, but it's not the same thing. So instead of it being about the type of fiber or about the properties of the fiber, it's actually about how it's buffered. So OS1 is what's called a tight buffered fiber. It's your standard patch cables is what you would see for indoor use. And OS2 is loose, and it's designed to be blown into ducts, so that when they have a duct and they lay new fiber into it, you blow it in with air. So your classic SMF, kind of the most common product that's out there, is what's called SMF28. That's actually a Corning brand name. It's not a standard. But there's lots of others. There's low water peak, dispersion shifted, non-zero dispersion shifted, bend insensitive. There's tons and tons of variants because this is the most prevalent type of fiber out there. So here's kind of a diagram showing you the difference, and you see how the core is smaller in the single mode fiber. And you see here in the multi-mode fiber, because it's so big, you're able to get these modal reflections. You're able to kind of have the light bounce around more inside the fiber, and that's one of your major limitations on distance. So single mode is what you use for all of your high bandwidth, long reach stuff. So now I'm going to go into the basics of optical networking terms and concepts just to kind of get everyone on the same page. So the very first thing I'm going to talk about is what's called optical power, and that's just the brightness of the light or the intensity. So what happens when you shine light down a fiber is over time, as that light propagates through the fiber, some of that energy is going to be lost. So that can be it being absorbed as it hits the glass particles and kind of gets converted to heat. It can actually not be perfectly reflected back into the fiber due to microscopic imperfections. And we call this loss of intensity attenuation, and we measure that in decibels. So it's the same decibels that you use when you're measuring sound. And a decibel is a logarithmic scale unit. So a decibel doesn't actually tell you anything on its own. It's what's called a dimensionless unit. So all it does is express a ratio between two other things. So the reason that we use a decibel is because I talk about Yeah, logarithmic value. So minus 10 dB, it's a logarithmic scale, so minus 10 dB is 1/10 the signal, and minus 20 dB is 1/100th the signal. So you see how we have that logarithmic scale. Another easy one, it's not entirely precise, but it's really close, is plus 3 dB is double, and minus 3 dB is half. So you can use that to kind of do your ballpark estimation. But remember, it doesn't tell you double of what. So when you want to talk about an absolute value, when you want to talk about like how bright is this relative to something, you need a reference. So in optical networking, that's called a dBm. So that's a decibel relative to 1 milliwatt of power. So for example, a 0 dBm signal is 1 milliwatt of power. That's an absolute value, that's a intensity of light. So 3 dB is 2 milliwatts, minus 3 dB is 0.5 milliwatts. So a lot of times people ask what actually should show up or what should happen when you have 0 light in the signal, and the correct answer is negative infinity dBm. That's what that is. But confusion between dB and dBm is probably one of the single biggest mistakes that you'll see in the real world. Just people don't know the difference between the two. People will work their light meters wrong. They'll be confused about which one they're looking at, and they'll just give you hideously wrong answers because these are two different ways to look at it. One is loss, and the other is or change, and the other is an absolute value. So be clear about the difference between the two. So why do we measure with a decibel? Well, light, just like sound, follows what's called the inverse square law. So think about it this way. A signal is traveling. So a signal travels distance x and it loses half its intensity. It travels another distance x, it loses another half of its intensity. So after 2x, you're down to 25% of your signal. At 3x, you're down to 12.5% of your signal. So if you use a logarithmic scale to explain this, then it simplifies the calculations. You can now do this with elementary school arithmetic. So you don't have to think about this in a logarithmic way. You can just think, oh, an x plus an x plus an x. I've gone from 3 dB to 6 dB to 9 dB. Very simple, very easy to think about. That's the only reason for using it. So here's a little table that people can reference later that kind of shows some of the conversions. But you know, when you get down into even 20 dB is only 1% of your signal left, right? So you very, very quickly have a fall off, and then when you start to get to these very, very low signals, that's where you see you've got almost nothing left. But technically 50 dB is still, you've got a tiny little bit of signal still left in there. So another concept in optical networking is called dispersion. So dispersion just means to spread out. So in optical networking, this results in signal degradation. So as the signal is dispersed, it's no longer distinguishable. You took what was once a 0 and a 1 and something that was very clear that you could look at, and you've now turned it into this blurred mush. So that's all that means. There's a couple different kinds of dispersion. So one of the most common ones you'll hear about is something called chromatic dispersion. And what's happening here is in a non-vacuum material, different frequencies of light propagate at different speeds. So this is actually how your optical prism works, right? So a higher frequency of light will propagate at a different speed than a lower frequency of light. It causes it to spread out. That's giving you that prism effect. CMD, called CMD for shorthand, is one of the fundamental limitations, and historically was a huge limitation in the optical systems and what kind of speed we could transmit. And it really becomes a limiting factor when you try to scale up with baud rate. And I'll talk more about what that means later, but this is just a fundamental concept of networking. The other major type of dispersion is something called PMD, polarization mode dispersion. And what's happening here is you've got this cylindrical fiber, but nothing is ever manufactured exactly perfect. So what happens is different polarizations of light will propagate faster. So you see here, you're looking at an X and a Y axis of this three-dimensional fiber, and at the end of some distance of fiber, the horizontal polarization might have arrived at a different speed than the vertical polarization. And that difference is called DGD, differential group delay. And that causes impairments to the fiber. It makes it harder to recover that signal. So in fiber optics, there's a couple of different transmission bands, different windows that we talk about. So there's really three big ones. 850 nanometer is what's called the first window. So this is your area of highest attenuation. It's really only used for short reach applications. So you see it today with these in data center, in cabinet type very short reach applications, but it doesn't do much more than that. 1310, the second window, is what's called the O band. So this was historically the point of zero dispersion. So dispersion as it goes through fiber changes depending on the frequency of light. So This was originally the spot that kind of had the least dispersion. It was the easiest to work with. So when people were starting to first deploy fiber optic networks, this was the band that people used. And you still see this used today for your kind of your medium reach, your 10-kilometer type applications. And you can do further with it. You can do 30, 40 kilometers on it if you really try. But more likely these days is people have moved to the third window, which is the 1550 nanometer window. And this is called the C band. That stands for conventional band. So it actually covers a range of 1525 to 1565 nanometers. It's the point that has the lowest rate of attenuation, so the least amount of loss over the fiber, which has kind of become the thing that we care about the most. And it's really, you're going to see this used for almost all of your long reach and DWDM applications. And then there's a fourth window called the L band, the long band, which is essentially a complete duplication of the C band, just a little bit higher up. And if you get into places where you're really constrained on fiber and you really want to double your capacity, you kind of have to put in a second set of every piece of tool to work with it, but it basically doubles your capacity on a pair of fiber by going into the L band. So here's a little diagram showing a difference between them, and you can see the progression of technology. So you see this dashed red line up at the top here. This is kind of showing the behavior of the fiber in the early 80s. So you see these different peaks. So the peaks are showing you the optical loss, the rate of loss per kilometer. And you can see that there's these certain peaks that were completely unusable because they were very high lossy. This was called water peak. So I'll talk more about that later, but this was a section of the band that was unusable, and you see how the windows were kind of adapted around those properties of the fiber itself. And you see the modern fiber got better and better and better until these days it's not nearly as big a problem. But that's kind of a lot of the reasoning for these original bands to have kind of been used. Another major concept, something that's really critical when you start talking about especially modern fiber systems, is what's called the OSNR, the optical signal to noise ratio. So really the difference here, the thing here is you're looking at the difference between the noise floor. So you see here we've got some amount of optical noise in the system and the actual signal. And the ratio between the two is your SNR. This is really one of the most determining factors on a modern system as to what you can do with the network. As long as you keep your OSNR high, you've got a good clean signal, you can continue to amp it, you can continue to do more things with it. Once that starts to fall down, that's where you hit problems. So it's a key concept. So now I'm going to talk a bit about wave division multiplexing. So WDM, we all know that light comes in many different colors. So when we look at light and we see white, we're perceiving it as white, but it's not. It's a mix of kind of all the other colors. So what happens when a WDM system is you can actually mix different colors of lights and on the same fiber, and they will propagate next to each other, ideally not interfering with each other, kind of traveling as ships in the night, and it lets you increase your capacity. So instead of only being able to carry one signal, you might be able to carry 20 or 40 or 80 or more. That's the concept. That's what we're going for, and you see here a little diagram showing the multiple colors of light being carried. So looking at the WDM channels, there's two main structures. Actually, it's probably not a terribly good diagram. I'll just go through this. So CWDM is there's two types of WDM out there. There's what's called coarse and dense. So CWDM is pretty much loosely used to mean anything that's not DWDM. So it's not a really hard to find standard. It kind of covers a lot of stuff. One popular meaning, especially historically, was something called 8 channels with 20 nanometers of spacing between them. So it's these very wide channels, and then if you were to add low water peak fiber, you got access to another 10 channels. So you tend to see this a lot. Like this was very popular back in the 1 gig days when it was much cheaper to make 1 gig CWDM than it was DWDM. But it can also mean a lot of other things, right? It can be used to refer to 1310, 1550 mux and kind of any other combination of light. DWDM is something that's actually well-defined. So there's an ITU specification that defines a grid of channels, and there's many different grids depending on the different channel sizes. So the common ones that you'll see out there in the world are 200, 100, 50, and 25 gigahertz. And the smaller the gigahertz, the smaller the channel. So your 200 gigahertz systems, this is kind of typically your 2000 era technology. You rarely see this in production anymore. It's kind of old. 100 gigahertz stuff that gets you your 40 to 48 channels, kind of depending on exactly how you do your channel allocation. This is something that you see very commonly. So you'll tend to see a lot of 100 gigahertz channels in metro deployments largely, especially where you're able to kind of buy passive muxes and tuned DWDM channels. The 50 gigahertz spacing is a lot more prevalent in commercial systems. So this gets you between 80 to 96 channels. So it's 0.4 nanometers between the channels, so it's much smaller. And then for a while, there was systems that used 25 gigahertz. You could actually get between 160 to 192 channels. And kind of what you saw happen in technology was we moved smaller and smaller and smaller. We moved all the way down to 25, and then we moved back to 50. Because what we were doing with 25 was cramming high-density 10 gig systems in. And then as we started to move to better technology, we were able to work better with wider channels. But these days, you end up with these modern systems that are very flexible. So you typically see systems that can be done in 12.5 or even 6.75 gigahertz increments. So what are the advantages? CWDM lets you use these cheaper, less precisely focused lasers, or more, they don't need to be cooled as actively. So what tends to happen is a laser will transmit on a certain signal, and then as it warms up, that will waver over time. And so if you have a cheaper laser, you don't need as good a cooling system, or you don't need to actively cool it. It just makes it a lot easier to produce. So if you've got this very wide window, the signal itself isn't inherently any wider, but it gives it more range that it can move around in. With DWDM, you get a lot more channels that are possible in the fiber. So all the way up to 160 to 192 versus 8 in a massively much larger chunk of spectrum when you think about kind of the classic CWDM. The other big advantage of DWDM is that it can stay entirely in the C-band, and that's a band that gets a lot of other properties. So one of the biggest ones is what's called EDFAs, erbium-doped fiber amplifiers. This is the range of frequencies where these work to amplify the light, make it brighter over time. I'll talk a lot more about this later, but that property lets you work with that in a much easier way. And this can all be duplicated again, like I said, in the L-band. Effectively, it's just a straight duplication. So here's a little diagram showing the kind of relative differences in size between the channels, and you can see here how wide a kind of a classic CWDM channel is. So like I said, there's a bunch of other definitions of it too. So some other things that you'll see kind of used for WDM. There's a classic 1310, 1550 mux. So you just take your two different bands and put them together over the same fiber. So it might let you use an LR and an ER optic together on the same fiber. These days we see a lot of work in what's called 4-lane gray optics. So what happens here is whenever there's a new technology, whenever there's a leap in speed, it tends to be much easier to implement it in parallel first, and then it becomes serial later. So you saw this when we moved to 10 gig. So some of the earliest standards that were much easier to implement was one called LX4. So what it was 4 2.5 gig channels inside rather than one native 10 gig channel. And over time it flipped, right? It came to a point where all the extra work of dealing with the 4 channels became more expensive and more difficult to work with than that native 10 gig. But still in the world of 40 and 100, we're still in a world where largely, especially on the client side, you need parallel optics to make it work. So 40 gig, for the most part, is really 4x10 when you actually look at it under the hood. That's all it is. And so it has these different 20 nanometer spacing grids. 100 gig, when you look at it, is largely 4x25 under the hood. And it has a different set of grids, and they're, of course, different just to be a pain. But you also see some other things out there. Single strand optics, there's a thing called BX, bidirectional. And what this does is it lets you, without having to have any other knowledge or expertise, take your pair of fiber and operate over one strand. So you could just instantly double your capacity, or you could work with a single strand fiber network, and it's just transmitting and receiving it at different frequencies of light and having a little tiny mux integrated into your pluggable transceiver. So a quick word about DWDM channel terminology. You see here's a diagram showing these different channels. So the width of the channel itself, the amount of signal that you can actually pass through it, is what's called the channel passband. And this matters because when you look at 100 gigahertz mux and it says 100 gigahertz, that doesn't mean you actually get 100 gigahertz that passes through that channel. That means that there is a 100 gigahertz spacing between channels. The amount of signal that you actually get through is the passband, and that can differ depending on different technologies. And different types of optics require wider or narrower passbands, or can be packed tighter if there's a wider passband. Like I said, when you see 100 gigahertz or 50 gigahertz, that's your channel spacing. That's the distance between center of both channels. The adjacent channel isolation is how much this filter is cutting off one channel from another. So there's a little bit of interference that can happen between channels, even when you've got an active filter trying to filter that out. Even inside of the channel itself, you can have variation. So within the channel, you can have portions of it that go up and down. That's called the ripple. And then the total channel isolation, really the signal from the noise floor, is what's called the total channel isolation. So now I'm going to talk about WDM networking components. So probably one of the most common prevalent things that you'll see out there is what's called the passive MUX. This is pretty much the first thing that you need to do any type of WDM. It's a simple, passive, unpowered device that combines or splits multiple colors of light. So you'll hear this called a multiplexer, sometimes a filter or a prism. Filters, historically, how it actually worked, and actually these days it's kind of gone back to being a prism, but it's either way, right? You're splitting or combining different colors of light. So in a complete system, you actually have both components. You have a MUX and a DMUX. Historically, these were separate components, and they still are, but they kind of work in either direction. So the technology works. It doesn't care whether it's receiving or splitting or combining or splitting. It works both ways. But you need two of them. And typically, you just see this sold in a single package. So here's an example of a simple little 1U component. An OADM is a system that lets you selectively add or drop channels without so you can pass a channel through undisturbed while adding or dropping others. So this is really useful when you're building these large rings. When you want to have multiple systems connected together, you want to be able to have an A and a Z talk to each other, but still have a B, a C, and a D in the middle that kind of drop signals. And when you build a kind of a well-constructed OADM ring, you can reuse the nodes, you can reuse the channels between different segments, you can do all kinds of nice things. But an OADM, a classic OADM, or what's called a FODM these days, a fixed OADM, is an entirely passive, unpowered device. It's very similar to a MUX, and just lets you add or drop certain channels. So a little bit about the actual technology that's being used here. So there's a couple different ways to make a MUX or an OADM. The three basic ones are the thin film filter, the fiber Bragg grating, and what's called an AWG, an arrayed waveguide grating. Thin film filters are kind of your older technology. They were really popular for your 200 gigahertz era type stuff, and they're actually still really useful. They're still good when you've got these low channel counts, right? So if you've got an 8-channel MUX or something like that, that's typically what you're going to see. And FBG is kind of similar. It's what's happening is you're etching inside the core of the fiber. You're creating this pattern that causes certain frequencies of light to be reflected. And when you pass it through this, it splits your fiber out. And AWG is really all of the modern technology. It's kind of how all of your high channel count systems are built. And it's actually really interesting how it works. So what happens is you've got these two what's called free space propagation areas. So it's basically this very wide prism that splits out all the light, and then you have two of these, right? You have one on one side, one on the other, and you have these many strands of fibers that connect the two, and they all have very precisely measured lengths that are slightly longer as they progress. And what happens is, as the light spreads out and propagates through these many different fibers and then comes back together, it constructively interferes or destructively interferes with each other, and that resulting reemergence pattern breaks the signal out into your 40 or 80 or higher channels. So this is really the highest end, the nicest system. This gets you your low insertion loss, and this is what almost all of your commercial MUXs are going to be these days. OADMs kind of moved beyond their classic fixed model into what's called a ROADM, a reconfigurable OADM. And what's happening here is it's literally just like an OADM, but you can log into a box and you can tell it to, instead of it being fixed only dropping these 4 channels or these 8 channels, you can tell it which channels to drop. So when you talk about a ROADM, you usually talk about it in what's called degrees. So the simplest example of an east and a west here, this is a diagram showing a 2-degree ROADM. So in this 2-degree ROADM, you have basically 2 options. You can either pass it through or you can drop it. And you see there's both sides, both degrees from both ends are doing that same operation. So there's a WSS, a wavelength selectable switch. It's a device that lets you steer the wavelength. And in this configuration, like I said, you have 2 options. You can either pass it to A or B. If you pass it to A, you send it all the way through. And if you pass it to B, you send it down to your mux and you drop it. But you can build these 4-degree, 8-degree, 20-degree ROADMs are now fairly common. So it lets you build these very complex topologies. You can have a central fiber hub, and you can just selectively route which pair of fiber, which path you're going to take. So you can build protected systems, you can reconfigure, you can do all kinds of more rapid provisioning. So ROADMs have evolved quite a bit over the years. So if you look at how a classic basic ROADM worked, like a first generation ROADM, really what it was, like I said, that WSS, that selectable ability to steer a wavelength out port A or B. But once you steered it, you sent it to a mux. You sent it to the same passive mux that you use historically for all of your other applications. So the downside of this is that it maps specific frequencies to specific ports. So when you say, oh, I need to go turn up a new channel, I need to turn it up on channel 31, you actually have to send a person into the field to plug a fiber into a port labeled channel 31, and that's the only channel that will pass through that. So as that started to evolve, people said, is there ways that we can eliminate the need to do that and make it easier to software reconfigure this instead of having to send people around to do everything? So the next evolution you saw was the colorless ROADM. So what this does is it effectively eliminates the need to map to a specific port, but you're still very limited to muxing or demuxing one direction at a time. So think of it like a replication, right? Instead of it sending the port, the color to one specific port, it sends to all the ports. But it still only lets you send to this one mux. So you get one direction, one thing, and if you ever want to change that, you have to still send someone out to the field to move cables. The CDC ROADM is really the modern ROADM. So it stands for colorless, directionless, and contentionless. So what's happening here is you get that colorless property where you can use any port that you want. You get the directionless property where you can actually steer, instead of it only being able to be passed through or dropped, you can say, I want this to be sent to my north degree or my east degree or my west degree. You get that flexibility. And contentionless means that the channel itself can be reused within the mux, and there's no inherent contention inside of it. So you might have channel 41 being used going east-west, and you might also have it being used going north-south, and the mux itself isn't going to care about that. So why do this? Well, the goal here is to be able to move to a system where this can operate entirely in software. So the transponders, one of the nice things you could do with this is you could reallocate the transponders, which physical path they go on, depending on things like time of day, fiber cuts, any type of operational need that you want. So the big advantage here is when you think about the cost of a transponder, the transponder itself is a very expensive component. And if you can have fewer of those out there and dynamically change it so that the same transponder can fill a link going east during its peak traffic time and going west during its peak traffic time, and you don't need to buy two, that's a significant savings to the network. So what's happening here is people are moving to a system where this can all be automated. So there's a system called PCAP, Path Computation Element Protocol, where the routers are kind of able to do real-time traffic measurements and say, hey, I know that I need to pass 17 gigs from this device to this device. It can take that information and send it offline to a control system that can then dynamically reallocate the optical waves. So basically the network is calling upon the optical layer to say, I need more or less capacity, and it can tune up and tune down. It can change the layout of these different waves over time. So potentially opens up a lot of flexibility, but it's also a lot of interop issues, and is historically always very difficult for the optical guys. So just to give you guys an idea of kind of what goes into a modern CDC ROADM, just to show you some of the complexity. So the very first thing that you have to do when you come into a ROADM is amp it, because you're going to lose a ton of power inside of a ROADM. So you go through, let's call it a modern 1x20 WSS, so you've just lost a ton of power going through this. So the very first thing you have to do is send it through another amp. So you have this array of amps. Basically, this WSS lets you send this signal to any one of these degrees, so you basically wire them all up. And then after you select which degree you send it to, which other degree you send it to, then you amp it again. So there's these arrays, these very large arrays of amps inside the system. And then it goes to what's called a multicast switch. So multicast switch is just literally an array of 1x16. So here's an example of an 8x16 multicast switch. All that is 8 different 1x16 splitters. So you take the light, you split it into, you have 8 different ways to split it into 16 different things. You spread this light out like crazy. And of course, you got to amp it again because it's now very dim after that. But at the end, you've taken this and you've replicated this signal to all of these different ports. So any one of them is capable of receiving the signal without having to be locked down to a specific thing. But you see, there's a lot of complexity, there's a lot of loss, there's a lot of amps that go into this system. So you pay for it too. So another concept in DWDM is something called superchannels. So imagine what happens if you've got a bandwidth requirement that can't be delivered in a single carrier. So what you can do with superchannels is pack multiple carriers together in a single channel. So it lets you get more efficient in your bandwidth. It lets you deliver a single data rate channel, even if your optical technology doesn't scale to support it, and all kinds of other nice things. So here's an example showing what would happen if I needed to build a 1 terabit carrier, a single carrier. I want a 1 terabit Ethernet port because Randy Bush is in the audience and he says we need terabit Ethernet. How would I do that? So you have a couple options, right? If I was to do that with a single carrier today, I would need this massive, I need like a 375 gigahertz wide channel. I would need 320 gigabaud modulation. I would need something that just doesn't exist today and probably won't exist for the next 10 years. But what you could do to solve the same problem is you use 10 different subcarriers. You can take 10 different components that we do have the technology to build today, pack them in together in the same amount of space, and deliver that same terabit Ethernet type client handoff if you wanted to. So that's what's happening at superchannels is you're using subcarriers to do different things optically. So DWDM channels themselves have actually evolved quite a bit over the years. So historically, they went in one direction, right? They went smaller. So you started at 200, went to 100, and went to 50, and went to 25. And then, like I said, after 25, you actually started to see it moving backwards. You moved back to 50, and now we're in a world where we want to go higher than that. And so the reason for that is, if someone says, oh, I need a 400 gig E, or I need a 1 terabit Ethernet solution, how am I going to do that? You can't pack that into a single small channel. So what we've moved to is a system called FlexGrid. What this does is it lets you, in software, reconfigure your MUX so that you have different channel sizes. There's no longer one uniform single channel size that propagates through the network. So if you've still got a legacy 10 gig system on there and it only takes a 25 gigahertz worth of the channel, you can give it a smaller piece of that spectrum. Meanwhile, if you've come up with something that is really high bandwidth and needs a much wider channel, you can give it that dynamic channel. And this can all be tunable, like I said, down into the 12 to 6 gigahertz increments. So this is what you see modern carriers deploying in any new system. It gives you that next-gen flexibility and protection. So now I'm going to talk about optical amplification. So optical amplifiers are a way to increase the intensity of the signal. So this happens purely optical, purely at a physics level. You don't need to regenerate the light. You don't need to do what's called an OEO. You don't need to convert back to electric and then back to optical. So there's different types, there's different things, there's different ways to do this optical amplification. So the 3 main things that you'll hear talked about, the 3 main applications, are what's called the booster, the preamp, and the inline. So the booster amplifier is something that's designed to be used right at your transmit. It's designed to work with really high power levels and to get the signal as powerful as it can before it goes out into the fiber. The inline amplifier is something that's in the middle. So it's designed to, it might not ever be going to a receiver, it's just a hut somewhere in the middle, and it's trying to make the signal brighter. And a preamplifier is something that's actually designed to be used on the receive side. So what you're going for here is you want something that works with really low input powers, you want something that does a minimal amount of noise, and you need to make it bright enough that your receiver can see it comfortably and everything can work. And like inline amplifiers kind of strike a balance between the two. So these are the 3 types that you see. So the most common amplifier that you'll see in the world is what's called an EDFA, an erbium doped fiber amplifier. So what's happening here is you've got a piece of fiber that's been doped with erbium ions, and it could be literally as few as 1 per millions and millions of atoms. There's somewhere in the silicon there's some erbium that's been mixed in there. And what happens is you have a pump laser. You have a laser of a different frequency that's injected into this piece of doped fiber via a coupler. When that pump energy comes in, it excites these erbium electrons. They move into a higher energy state. And then when you have a 1550 nanometer, when you have the C-band colored photon come along and hit one of these excited erbium ions, that electron jumps to a lower state and it simultaneously emits a clone of the photon at the same frequency in the same direction with the same properties. So you've made the signal brighter. So there's two states. There's what's called the unstable state and the quasi-stable state. So there's two different colors of optics that will do that, and your best ones will actually use both. But so the two frequencies are 980 and 1480. So why can't you use this to kind of clone a signal forever? Well, in addition to making the original signal brighter, you also generate something called amplified spontaneous emission, or just noise. So the way this works in physics is whenever you've got this excited erbium ion, you've got it now at a higher state, and about 10 milliseconds is the number. Once 10 milliseconds have gone by and this excited electron hasn't encountered a good photon, it spontaneously decays and emits a junk photon. And this is now noise. It's not any part of the signal. It doesn't do anything good. And once it's generated, you can never pull it back out. It's now a part of the signal. It's indistinguishable from the original. And after enough hops, you ruin the signal. So here's a diagram showing kind of what that gain profile looks like. And you see there's two channels here that have been amplified, but everything else that you see here, that's noise. That's junk that's been injected into the system. So why does this really matter? Well, what I'm trying to show here is one of the properties of OSNR. Like I said, OSNR is one of the most important things when you think about how do I get a long-reach system. And really what you're fighting here when you're fighting noise is what power level did you receive the signal at? So if you let the signal get really low before you amplify it, you create a ton of noise. If you amplify it before the signal has gotten really low, you create very little. So you see here, this top line, we start with a 24 dB OSNR. It's a very, very good, very strong signal. And you see that we amplify it 10 hops, but we never let the signal get below -5 dBm before we amplify it. You see that we have almost no loss in OSNR at all. And you see, as we move to 10 dB and 15 dB and 20 dB, you see how quickly this falls off. And then if you let the signal get down to -25 dBm before you amplify it, you see here that at the end of 10 hops, we've gone from 24, a very strong signal, down to 17, a relatively weak signal that wouldn't support some of the modern technologies. So when you're designing a system, you're always thinking about how do I amplify before I let the power levels get too low. That's why all of this matters. Another type of amplification that's different from EDFA is what's called Raman. So it works on a principle called stimulated Raman scattering, which I'll talk more about later. But what's happening here is you've got, instead of a piece of fiber that's been doped, you're actually using the line side itself. It's something called distributed. So you're actually using the transmission fiber as your gain medium. So instead of you injecting a pump laser into a, it might only be a 1 meter of fiber that's sitting inside of your mux, you're injecting a pump laser out into your long haul transmission system. And as it goes out into the system, it encounters the real signal and it causes a transfer of energy. So the pump signal is depleted and the original signal that you're trying to amplify is made brighter. And you see here the three stages as that happens. And the most common application that you see when you do this in Raman is something called counter-propagating. So what's happening is you're actually shooting the laser the opposite direction of the propagation of the signal. So here's why this matters. In an EDFA-only amplification, here's an example where you start with a very high power level and it declines over time as you propagate through the fiber, and you hit an amp and you amplify it again, you make it brighter. The two areas that you want to avoid are too high a power and too low a power. If you go too high, you get into what's called nonlinear effects. This is where that you start introducing all kinds of weird properties that aren't easy to predict and aren't easy to deal with, that start to cause impairments in your signal. But if you let the signal get too low, that's where you start to introduce the high noise. So this is showing an EDFA amplification. You see the penalties that you're going to pay here. You had to launch at a very high power to get it out, and you had to receive at a very low power before you amplified it, so you've lost a lot of OSNR in the process. In a hybrid EDFA Raman amplification, what happens is you add a Raman pump and you send it the opposite direction. So you're sending it back the opposite direction that the signal is coming in. And what happens is it actually makes the signal get brighter within the fiber. So you see here in this red diagram that you needed to launch at a lower power. So now you've stayed out of the zone of nonlinear effects. And then as it started to get closer and closer and closer to the end, it encounters the Raman pump and it starts to get brighter and brighter and brighter. So by the time you receive the signal, you've now received it at a much higher strength. You've now avoided that noise that was being introduced. So this is very important. This lets you get much longer reaches and keep much higher OSNR and lets you do more data over longer distances. So how much does it matter? Well, look at this example. Let's assume that we've got a 21 dB OSNR signal, and we've got 23 dB of spacing between these things. That's kind of your 100 kilometer between huts, very, very common. In an EDFA-only system, we were only able to do 7 hops. We were only able to do 700 kilometers. As soon as we add Raman to this, we're now able to go to 2,000 kilometers. We're now able to get to 20 hops. And in fact, you can probably do better because this is assuming a very, very high OSNR, and technology has actually gotten quite a bit better. But you see here, because you were able to amplify with the Raman, the signal, you no longer need as much gain on the EDFA when you send it, and you've kept that higher OSNR. So another big thing that comes into play when you think about amplifiers is power balance. So it's unbalanced channel powers cause all kinds of problems. You have a system that's not stable. And one of the problems is that amplifiers, the amount of gain that they introduce varies across the frequencies. So the very first thing that you see happen to compensate for this is something called a gain flattening filter. So this is really a static attenuator that's designed to kind of match the gain profile of the EDFA. And it's really engineered, it's very specific to the EDFA itself. So when a manufacturer makes the EDFA, they look at the gain profile that they get out of it, and then they design that gain flattening filter to be the inverse of it. So what you're trying to do here is, you might have had this one channel be much brighter and this other channel be much lower. You want them all to be consistent and flat. So you flatten them all out till they're all about the same frequency. But even these very small power variations that are going to sneak through this add up over time. So eventually you need something called DGE, dynamic gain equalization. And it tends to be, every 7 or 8 hops or something like that. But as these, over time, as these different amps start to incur these little bits of variation, you end up with a couple of dB of difference between your channels, and that causes problems. So typically what you see in most networks is you use a ROADM to fill this role, but you can use other things as well. But every so often you need something that's actually aware of the content, that takes a look at it and rebalances the channels as well. So amplifiers also have limits in their total system power, both in what they can output and what they can input. So this matters because the total input power changes over time as you add channels. So imagine you've got a single channel and you're sending a +0 dBm, so you've got 1 milliwatt of input power. Now you go to a DWDM system where you've got 40 channels, and each one of them is outputting the same amount of power. So you've now got 40 milliwatts of power. That's plus 16 dBm of power. That's actually incredibly bright, strong light. So if your amplifier has a maximum input power of -6 and you run all 40 channels, that means before you put the channel into the amp, you needed to attenuate it all the way down to -22. So you need to think about these different types of amplifiers and the different power balance requirements for the channels to make the system work. The other thing that happens is this can change over time as you add or lose channels. So imagine you're in a situation where you've got these 40 channels going through, and now all of a sudden your data center loses power and you lose half your channels. Suddenly the power levels across this amp system have changed dramatically. So you need a system that is able to react to that quickly. And a good EDFA will have a constant monitoring loop that will look at the input signal, look at the output signal, and will make adjustments dynamically to keep the power levels right. And the best EDFAs will actually communicate with each other. They'll have a communication channel band, they'll talk to each other, and so it'll know what the EDFAs upstream are doing, it'll know what it's doing, and it can communicate and adapt to changing fiber conditions and splices and things like that without you ever having to go in and configure things. So some other optical networking concepts here. I told you it's a lot of material. So one thing you'll see out there is something called an optical switch. And what's happening here is it's letting you move the light around between ports without doing that OEO conversion, without going from optical to electrical back to optical. So the most common design that you'll see is something called 3D MEMS, and it's basically an array of these tiny little mirrors that are controlled electrostatically. And so you can very quickly, within milliseconds or less, steer these mirrors. So you can take a mirror and take a channel of light and say, I want it to go to port 1, and 50 milliseconds later, I want it to go to port 10. So you can use this for optical cross connects. You can use this for fiber protection. Probably the most common area that you see it where it makes the most economic sense is people who do lab work, where you've got a system where you're constantly moving and reconfiguring cables. It could very quickly pay for itself. I talked earlier in the ROADM about the WSS. That's a component called the wavelength selectable switch, and it lets you route these individual wavelengths across ports. So the first generation WSSs use these 3D MEMS technologies, and then as we move to more modern ones, they actually use what's called LCOS, liquid crystal on silicon, where you're kind of able to dynamically steer these beams of light. So there's a lot of very interesting physics that are going into these high-end ROADM systems to make all this work. There's a component out there called a circulator that's typically not seen by the end user, but you use it quite a bit in manufacturing these components. So the way a circulator works is it has 3 ports. So when light comes in port 1, it goes out port 2, and when light comes in port 2, it goes out port 3. So here's an example of using a Bragg grating filter combined with 2 circulators to create an OADM. So you see when the light comes in from the left side here, it goes out to the right, and when it hits the Bragg grating filter, which only reflects certain frequencies of light, it sends it back and it sends it to the drop port. So here you get this behavior of I want all these frequencies to propagate except for this one frequency which matches the filter. That sends it back and out of drop port. And you see these used in other systems. You'll use them quite a lot when you're building single-strand systems. You'll see them inside muxes. You'll see them inside dispersion compensation spools, so you get to reuse the same fiber twice. You'll see them inside amplifiers for the same thing. There's another component out there called an optical splitter, and it does exactly what it sounds like. It splits the signal. So some really common examples of things you're going to encounter in the real world. The 50-50 splitter is typically what's used for your very simple optical protection. So the philosophy here is you take your signal and you split it in half, and you send it down 2 different fiber paths. And then on the other side, you've got an optical switch, and all it's doing is looking at power levels, and it's using whichever side is the strongest. So it might be using side A because that's your short path, that's where your strongest signal is. And now let's say you go out and get a fiber cut and that line goes down. Within milliseconds, it can detect the loss of power and it can switch to using the other strand. And you did all of this for a 3 dB hit, right? 3 dB to split signal in half. So it's a very cheap way to protect. Imagine you had terabits of bandwidth. You had dozens of transponders or hundreds of transponders and millions of dollars of components. Rather than having to duplicate both of them to light both systems, you could throw this very simple component in and use both sides of the fiber to get that active protection and deal with fiber cuts. Another thing that you'll see out there is the 99.1 or the 98.2 splitter, and this is often used for what's called OPM, optical performance monitoring. So what's happening here is you're tapping a very small portion of the signal and you send it over to a little spectrum analyzer. And that spectrum analyzer looks at what's happening. It can tell you what your OSNR levels are, what light channels are in use, what power levels are. It gets you insight to your network without you having to send a person out there. So very, very helpful when you're troubleshooting things. Another major concept is becoming increasingly important is something called FEC, and that stands for forward error correction. So what's happening here is you're adding extra redundant information to your transmission so that when the receiver gets it, it can actually computationally recover from any errors that it sees. So think of it like RAID 5 for wavelengths, right? You've added a little bit of extra information, but in the event of data loss, you can computationally recover it. So in practice, what happens here is you use FEC to lower the required OSNR. So you take a signal that otherwise would have been completely unusable because it's gone past the point of being able to be decoded, and by adding a little bit more overhead, you can now make it go much further. So a really common example is you can take a 10 gig signal and pad it by 7% and make it go from 80 kilometers of reach to 120 kilometers of reach, not by doing anything other than making it possible to kind of recover that signal better. So where this really matters is when you're kind of upgrading old DWDM systems. As the problem is, it's usually not practical to go out and move your huts closer. Moving huts is a huge construction operations, costs lots of money. You really don't get much flexibility when you're doing that. So when you want to move to a new generation technology, an easy way to solve that problem is to make the FEC systems better. So what you've seen here, there's 3 generations of FEC. The first generation, typically something called RS FEC, Reed-Solomon FEC. So you tended to see like a 6% overhead, and you got about 6 dB of what's called net coding gain, or 6 dB more signal that you were able to work with versus what the base signal would have been for OSNR requirements. When you went to second gen, you added a little bit more. You went to 7% overhead, but you got 8 to 9 dB of gain. Then when you went to third gen, you moved up quite a bit. You move into something called SD FEC, soft decision FEC. So you're adding a significant amount of overhead. You might add 20 to 25% more data to the encoded data. But that's getting you a 10 to 11 dB gain of OSNR. That can actually be huge. That can make the difference between a system working or not working. That can make a difference between a system that can do 100 gig per channel or that can do 200 gig per channel. Quite easily. So it's worth it to kind of put all that extra data in. And you see FEC has actually become very critical to even kind of commodity pluggable components as well. So things like 100 gig SR4 technology pretty much require FEC to work. Even though you're only going a few meters over a local patch cable, you've kind of got that built in. And you'll see that more and more and more. Most systems have to have FEC built in just to work with kind of these commodity optics. So here's a diagram showing the benefits that you get from these different levels of forward error correction. So you see here an unencoded signal. What this curve is showing is as the OSNR, as your x-axis gets further to the left, your OSNR is going down. You're moving up this curve of the bit error rate. So you're getting more and more and more bit errors, and this happens in an exponential curve. So in a completely uncoded signal, you might need, in this example, an 18 dB OSNR to get this low rate of bit errors that you want. By moving to different generations of FEC, you see how far back we've pushed it to now maybe I only need 9 dB of OSNR to get that same performance level. That lets me get much, much, much better performance out of the system. Another thing that you'll see referenced when you talk about optical technology is something called OTN, Digital Wrapper Technology, or G.709. So this stands for Optical Transport Network, and think of it as a replacement for SONET and SDH. So what it's giving you here is the ability to mux and demux at a TDM level. You're able to take, for example, a 100 gig wave and turn it into 10 by 10 by taking these individual components and putting it inside a larger channel. So historically, SONET and SDH were completely wavelength unaware. They didn't know or think anything about WDM. So OTN technology makes it so that they are aware of this. You can, like I said, take its 100 gig service, break it up into 10 by 10, and for the most part, when you buy a 10 gig wave, you almost never get it as a 10 gig wave. You get it as 1/10 of a 100 gig wave, that kind of thing. So it lets you mix multiple protocols inside the same wavelength. It helps with troubleshooting. And just think of it like a SONET SDH extension. So now I'm going to talk about all the many, many, many different types of single mode fiber out there. So I already discussed that single mode fiber is really essential for all of your long reach applications, but there's many different types of it. So the most common types that you'll see out there, these are the basic standards. So your very common basic standard single mode fiber is what's called ITU-T G.652. You might hear that called SMF28. Like I said, that's a Corning brand name, but that's a very common name because it was one of the most popular fibers of its type. You saw an evolution to what's called full spectrum or low water peak fiber. So this was just that same type of fiber, but now we removed those water peaks. We started to make those certain frequencies that were unusable before usable again. And you see it's actually the same standard, it's just a newer version of it. So as we move to new versions of G652, they got better and better and better about removing that water peak, and that's mostly what you see out there. Then there was a technology called dispersion-shifted fiber, G653. That turned out not to be a terribly good idea. So then there was a technology called non-zero dispersion-shifted fiber. That was G655. There was a low-loss fiber. So G654 is typically what you see for oceanic systems, undersea cables. We were very specifically concerned about low loss because you really don't have a way to go in and kind of swap out cards or get access to the fiber once it's in the water and you've got those amps out there. And then you've got another standard called G657, which is your bend-insensitive fiber. So your standard single mode fiber, this is the fiber that you saw that was kind of out there in these original fiber cables. So if fiber was kind of deployed in the 90s, you can almost guarantee this is what it was. Like I said, sometimes called SMF28. You'll also see it called NDSF, non-dispersion shifted fiber. So just kind of basic fiber. And this was originally designed to be used by the 1310 band, as I said. So this all happened before WDM was ever a thing, right? In fact, this fiber was deployed before amplification was even discovered or available or commercialized. So ironically, what's happened here is we've actually gone full circle. We've gone to creating all these different fiber types to try to optimize the network. To these days, this standard fiber is actually the preferred type of fiber to do high bandwidth systems. So ironic. The low water peak fiber. So what I talked about earlier, those water peaks, what happens here is you get these hydroxyl molecules that get into the glass during the manufacture of the fiber, and they absorb certain frequencies of light. And the manufacturing techniques just got better and better and better to kind of remove those, and you see the removal of that water peak or turning it into something that's very low. That's all it is. So dispersion-shifted fiber was an attempt to improve the situation. So what happened here was they engineered the fiber in such a way that it moved the point of zero dispersion over into the 1550 nanometer band. So they thought, this will be great. We'll have now fiber that I can send low dispersion and low loss, and everything will work great. And it turned out to be a really bad idea. So this worked well for single channel systems before the advent of WDM. And the problem when you start doing any type of WDM on the system is it causes a lot of nonlinear interaction. I'll talk a lot more about that later on, but basically this type of fiber was a giant dead end, and you almost never see it in the real world. It's pretty much used for pull string and nothing else. So then they said, well, all right, how can we do this, but how can we fix this? So they moved to something called non-zero dispersion-shifted fiber, which is very similar in concept, but they moved that point of zero dispersion so that it's just outside of the range that you're actually sending your signal at. So you still get a little bit of dispersion, but it's not, it's not nearly as high as it was, but it's not zero. So then to manage this, to compensate for dispersion over time, what you have are two different types of fiber. So you had a plus and a minus. What happens here is these have different slopes. So your transmission fiber will cause the signal to spread out over time, and then at the end of the transmission, you'll come to somewhere where you compensate for it, and you basically run it through a spool of fiber that goes the opposite direction, and it recompresses it. So with physics, purely at a fiber level, you've kind of compensated for that dispersion that happens over time. That was how a lot of 10 gig systems were built and operated. So other common fiber types that are out there, like I said, G654 is your ultra low attenuation. Really what it's designed for is to be able to send really high powers. So I'll talk more about this later, but it has a very large core. It has a very large effective area, so it lets you transmit really high powers without nonlinear issues, and you see this used for undersea cables. And G657 is your bend insensitive fiber. So this is the stuff that you'll see at data centers. This is the stuff that you'll see anytime you have humans around it. And if you just have regular fiber, it's actually very sensitive to being bent. If you bend it just a little bit too far, the light will actually leak out the sides. So you really want your patch cables to be made from G657. It's pretty much the only way to do kind of patch cable type stuff. And remember, modern fibers are actually much better than some of these original specs, but also remember that lots and lots and lots of fiber that's out in the ground is old fiber. So here's a diagram comparing kind of the different rates of dispersion for some major brands of commercial fiber here. So you see the top one, the 652, that's your classic SMF. You see that it's got this very high rate of dispersion. So the magic number for kind of the center of the C-band tends to be 18. The unit of measure here is called picoseconds per nanometer. So you see about 18 as very common. And then there's different types of dispersion shifted fiber. So Teralite, True Wave, Leaf. They each have different slopes, but you see how they're trying to reduce that rate of dispersion. So now I'm going to talk a bit about nonlinear impairments. So this is a fun little piece of physics. So what do I mean when I say nonlinear impairments? Really a better description here might be high power problems. If you don't transmit at high powers, you will never have these problems. Why do you care? You want to transmit at high powers, because if you transmit at a high power, that means you receive at a higher power. That means you introduce less noise. That means you can continue to amplify for longer. So you do want to push it as far as you can. But so what do I mean by high power? Well, usually the magic number is somewhere in the +4 dBm per channel. So you actually have to be pushing it. It's not something that you will see in your regular life if you're using kind of even a hot optic that's a single output. You really have to put it through another amp first. So there's two main types of nonlinear impairments out there. The first type is called stimulated scattering, of which there's two types. The stimulated Brie-Wan scattering called SBS, and stimulated Raman scattering called SRS. And the other type is called the Kerr effect. So what's happening in the Kerr effect is the intensity of the light, if the light gets bright enough inside the fiber, it actually dynamically changes the refractive index of the fiber as the bright signal comes in. So it causes a couple different things. The three big ones are what's called four-wave mixing, self-phase modulation, and cross-phase modulation. So SBS is actually really interesting. What's happening here is when you start to fill this fiber with lots and lots of optical power, you actually start to make the atoms vibrate, and they start to vibrate in a pattern, right? And as they start to line up and as they start to kind of cause these acoustic waves, it actually creates a dynamic Bragg grating inside the fiber. So it actually causes your optical signal, instead of continuing to propagate through the fiber, it actually starts to be reflected back. So past a certain point, instead of any more power getting into the fiber, all you're doing is causing that power to be spit right back out at your transmitter. And that can cause anything from errors to actual damage on the transmitter, so it's a bad thing. But the SBS is really dependent on the power density of the fiber. So what's happening here is the wider the signal, the wider the line width of the signal, the more you spread that optical power out. So as we move to modern systems, kind of 100 gig, 200 gig and higher systems, we've moved to a system that spreads that power out quite a bit. So where this used to be a huge area of concern for 10 gig signals, it's not nearly as much anymore because you've got the power dispersed over a wider signal. So another reason that matters is when you think about dispersion and why dispersion causes some of these effects. Dispersion is causing that power to be spread out. So very quickly you have this high power in this one specific frequency, and over time it spreads out. So it reduces the impact of this issue. But if that power doesn't spread out, if the signal is not dispersed, then that's where you start to see these. So SBS really kind of requires long fiber distances to see. So if you put a really high power system, but you do it through a 1 meter patch cable, you probably won't notice. But if you do it through a 20 meter patch cable or 20 meter fiber or 20 kilometer fiber. So 20 kilometers is kind of the magic number. Once you go past 20 kilometers, the signal has fallen off below the point where it's causing that impact. But for that first 20 kilometers, you're starting to get those reflections all the way through. So SRS, stimulated Raman scattering, is a very similar phenomenon, but what's happening here is when you put too much power into the system, it causes power to be transferred from one frequency to another. When you do this intentionally, this is how Raman amplification works. When you do this unintentionally, you cause noise. So ironically, actually making the channels tighter reduces the SRS effects. So here's some example launch powers showing different, so non-zero dispersion shifted fiber being the worst case scenario for this, showing the different power levels. So if you're trying to send 80 channels and you're sending them down a 50 gigahertz spacing system, you can only transmit 0.5 dBm per channel, and past that you're going to start to see impact due to SRS. Four-wave mixing is a really cool issue. So what happens here is when you have channels that are regularly spaced, they actually interact with each other and they create harmonics. So the closer they're spaced, the worse this effect gets. So you see here we have 3 channels that are regularly spaced. And what happened is the interaction, the nonlinear interaction, because of the high power levels and because of the low dispersion, caused it to create noise, harmonics, both in band in these 3 channels and on the side bands, even though those side bands aren't being used. So this is a completely transmission rate independent behavior. It's just a property of physics. An easy way, or one way to kind of deal with this, is to have uneven channel spacing. So rather than have things lined up precisely in rows, you can kind of move them around a little bit. But remember, this is really prevalent on low dispersion fibers. So here's an example showing why that is. So if you look at this top line, this is an example of a 0 dispersion fiber. And you see that you go all the way out to, so 0.8 nanometer spacing is a 100 gigahertz channel. And you see that at 0.8 nanometer spacing, we're basically causing huge amounts of mixing. This is the mixing efficiency, so how easy it is for these signals to mix. Even adding a single picosecond per nanometer of dispersion causes this to be greatly reduced. So you see that we went from massive efficiency in mixing down to a negative 30 dB of efficiency. But then you see that if we had standard single mode fiber with a high dispersion rate, that it would be even lower. It would be down into the negative 50 and effectively not be an issue. So this is an area where dispersion is actually a good thing. So I have some examples here of different things that you can look at over time. So the next ones, the Kerr effects, are what's called the interchannel effects. So cross-phase modulation is what happens when one wavelength of light affects the phase of another, and it causes interchannel crosstalk. So probably the most common area you'll see this in real life is when you try to mix like a 10 gig and 100 gig technology on the same fiber. You're mixing what's called an NRZ system. I'll talk more about this later, but you're mixing an amplitude modulated only system with a phase modulated system, and the 10 gig signal causes noise on the 100 gig signal. So it actually, it doesn't hurt the 10 gig signal at all, but having 10 gig signals on your fiber will cause impact to your 100 gig signals. And here, having a high chromatic dispersion actually helps prevent this. Self-phase modulation is what happens when the change in power level between a 0 and 1 is so extreme that it causes the Kerr effect. It causes the change in refractive index to happen dynamically in the fiber. And what's really bad here is you end up with a property called self-focusing. So imagine that inside of this waveguide of fiber, you create a smaller waveguide of fiber, and you focus the power because of these different refractive indexes. And in this example, having lower chromatic dispersion helps with SPM. So all of these things are a balance. But ultimately, all of these nonlinear effects are all about power and power density. So one of the really easy ways to defeat the entire thing, besides just transmit at a lower power, is to have wider fiber, more fiber that you can spread the power into. So this is something in the fiber called the mode field diameter, the MFD, or you'll see it translated into the fiber's effective area. And if you don't see the effective area, it's literally the mode field diameter pi r square. So if you get a wider effective area fiber, so here's an example, kind of using your very standard non-zero dispersion shifted fiber, you might have 50 microns squared worth of effective area. And Leaf and some of the better dispersion shifted fibers made that a little bit better. But your classic SMF28 is better still, right? It's a wider fiber. So you're able to put higher power levels into the fiber and not cause these issues. And then your submarine fiber is the best of all. This is a system that's pushing right up to the maximum boundary of what can still be a single mode fiber. But by having this very wide core, you're able to inject much larger amounts of power. One trade-off here is that the larger the effective area, the less Raman gain you get. So if you depend on a Raman system, you need to take that into account, that I'm using this large effective area, I can transmit at a higher power, but now I get less gain out of my Raman system as well. So a quick word about what we actually transmit over the fiber. So very first thing we're going to talk about is modulation. So remember, at the end of the day, everything that we do is an analog world. We think we've got these beautiful digital signals, but we still have to send it over an analog system. And light is really just another type of electromagnetic wave, and it propagates in a wave-like fashion. So the very simplest form of modulation, the system that you see that's in use for effectively all of your 10 gig and lower systems or signals is what's called IMDD. That stands for Intensity Modulation with Direct Detection. And the most common version of that is something called NRZ, which stands for Non-Return to Zero. You'll also see this whole type of system called ASK, amplitude shift keying or amplitude modulation. It's like your AM radio. You're modulating signal by increasing and decreasing the power level. And all of this is just a really fancy way of saying bright for a 1 and dim for a 0. That's all this is. And direct detect just means that all you need to detect this is a photodiode. You look at the light and you see, I saw a bright, I saw a dim. You turn that back into a 1 or 0. So historically, like I said, all these fiber systems up until very recently have all been based on this technology, and all we've done is signal faster and faster and faster. So the signal rate, the rate at which we actually change a signal, is what's called the baud. So technically, it's defined as the symbol rate per second. So when you see a 10 gig signal, so you go out and you buy a 10 gig Ethernet port, what's happening is you're actually flashing from a bright to a dim 10 billion times per second. That translates into gigabaud. So in this case, it's a direct mapping. We encode 1 bit per baud. We have a bright or a dim, so we know a 1 or a 0, and we just change the speed at which we flash the light really quickly. And that worked well to a point. We built a lot of very successful networks with it, but it really only worked up until about 10 gig of technology, and then it kind of started to peter out. But obviously we needed more bandwidth than that. So what's the sad internet to do when we can't keep up with our cat pictures? Well, we start looking for ways to increase the amount of information that we can encode per symbol change. So there's a couple different ways you can do that. In the world of ASK, in the world of amplitude keying, the easy way to do that is introduce more than 2 states. So instead of having a bright and a dim, we now have a bright and a really bright. So you can encode more information with different levels of state. And the other method is to move to something called phase shift keying. So that's modulating on a property of the analog signal called the phase. So what's happening here, think about an analog signal represented as a sine wave, and it goes from a high to a low and propagates. What you can do is modulate on the difference in phase, the offset between where that peak and that unpeak is. So what you do is you have a receiver that is actually specifically looking for it. It's locked onto the phase that it's expecting to see, and it can calculate the difference between what it thinks it should be receiving and what you're sending, and you're able to encode data that way. So you can actually start to pack a lot more data into a system without having to just rely on brightness and dimness. So that introduces something called coherent optical technology. So coherent comes from the concept called phase coherence. And what coherence means is the ability to measure phase change over signals. So like I said, what happens here is you have a known reference signal. So on your receive side, you actually have a laser. And you configure that laser to be exactly what the transmit side should be, and you compare the difference between your local oscillator and what you receive. You're able to calculate phase information, and you're able to encode data in an entirely new and different kind of way. And this is what helped us break the 10 gig barrier, kind of in the 2011 area timeframe. So tying all this together, doing phase shift keying is not actually as easy as it sounds, because with amplitude keying, all you needed was a photodiode, right? All you needed was to see a bright or a dim, and you could make a decision of a 0 or 1. But doing phase shift keying actually kind of combines a lot of different things. So to do it, you need a purpose-built DSP, a digital signal processor. So this is just a microprocessor that is specifically designed to do real-time processing of signals. And they tie all this information together. They make it usable and coalesce it into some kind of useful data. So when we introduced coherent technology, you basically saw a jump from kind of the previous limit, the wall we were hitting our heads against, of 160 10 gig channels, to immediately moving to 100 gig channels and to 9.6 terabits per fiber. So a huge jump in capacity. Like I said, it delivered true 100 gig optical signals for the first time. It eliminated the need for physical dispersion compensation, because the property of being able to modulate on phase kind of lets you calculate what that dispersion is and lets you compensate for it. And it enabled these really high bandwidths over these really massive distances. So then what do you do when you need to go from there? Well, then you start tying the two together. So you move to a system called quadrature amplitude modulation, or QAM. And really all this is using amplitude modulation and phase modulation at the same time. So take two amplitude modulated carriers, send them at the same time, and do it with an offset. Do it with a sine and a cosine offset. And then rely on your DSP to kind of computationally recover all this data. So we create more and more complex versions of this over time. You can add different possible states. You can add more bits per symbol. So you see in the real world today 8 and 16 QAM. Very soon you're going to start to see 32 QAM systems, and then there's already 64 QAM and higher systems in development that are going to be out very soon. So another thing that you see in these modern commercial systems is something called polarization multiplexing. So remember that light, the many things that we don't really understand about what it is, it's an electromagnetic wave propagating through space. It can actually do that in three-dimensional space in two different polarizations. So you can have a horizontal and a vertical polarization of light. The two will pass each other and not interfere with each other and propagate differently along the x and the y axis of the fiber. So in a modern system, what happens is you actually take two different lasers and send them at two different polarizations and mux them together. So it kind of gives you that double the capacity for the same pair of fiber right off the bat. So when you look at a modern system and you think about what is the bit rate, what is the amount of data that I'm able to get, basically think of it as a multiplication of polarization times baud times modulation. So your polarization, like I said, today we have dual polarization, and you'll double capacity, and we're already looking at things like optical angular orbital momentum and all kinds of different ways to multiplex additional properties of light. But today we kind of get two polarizations, so you get a doubling of bandwidth. The baud rate, the higher the baud rate goes, the wider the channel size that you need, and the better the DAC needs to be. So today, very, very common systems that you'll see are kind of in that 32 gigabaud range, and we're starting to see technology come out to move into the 50 and 60 gigabauds. But as you do that, you need wider channel sizes. Modulation is when you're encoding more data per baud change. So for the same signaling rate and the same everything else, you can encode, instead of being 4 bits per symbol, you could be 5 bits per symbol, but it's harder to detect. So basically with modulation, you need better OS&R levels to make all this work. So when you're building a system, you're trying to strike a balance. You're trying to say, let's say, for example, I want to do a 100 gig signal. I could very easily do that with DP-QPSK, and I can do that tens of thousands of kilometers. So 10 dB OS&R is very low. So I can do that for very long distances. And I only need 37.5 gigahertz worth of channel to do it, but I only get 2 bits per symbol per hertz of efficiency. So I'm transmitting a 128 gig signal with FEC. I'm getting down to 100. That's what I'm able to get out of it. So now you say, well, what if I want to move to 200 gig? Well, there's a couple ways you could do that. One is you do a 32 gigabaud 16 QAM system. So this is very common in a lot of the DCI boxes that you'll see from folks like Infinera and Corient and Nokia and folks like that. It's all very similar technology. And it requires a 19 dB OS&R. So that can either mean anything from a few hundred kilometers to a couple thousand kilometers, depending on your line system, but it's a much higher OS&R requirement. The other way that you could do it would be to have a lower modulation, move back to 8 QAM, but to do it at a higher baud rate. So for the same effective data rate in the end, you could do it at a 56 gigabaud rate. This now needs a 62.5 gigahertz channel, but maybe you don't care about packing the maximum number of channels in, so you're able to use this wider channel to support it. But now you're able to get the same 200 gig signal and take it down to a 17 dB OSNR. So this might let you get hundreds of thousands of kilometers more distance out of it by doing it in a different way. And you see the technology that we'll probably be doing by the end of the year, or certainly into next year as people ship new systems, is the 64 gigabaud 64 QAM. So this is purely a metro application for the most part, but you'll be able to get 600 gigs per wave. So this is what's going to support 76.8 terabit systems. Expect that to be out within certainly under a year widely. So a couple more things about coherent. Like I said, it eliminates the need for that physical dispersion compensation because it's able to computationally recover for it. So you went from a world where you might have been limited to a couple thousand picoseconds per nanometer to one where you can now do hundreds of thousands and not care. And in fact, coherent systems actually work better with dispersion. And as well, the nonlinear effects are better with dispersion. So this is why we've kind of moved back to going back to classic single mode instead of any of these other things that were created for 10 gig technology. So another cool thing with coherent is that because of the property of having a local oscillator and knowing what you're looking for, you can actually lock on to one specific frequency and ignore everything else. So this is what makes your CDC ROADMs work. All you're doing is taking the signal and sending it out every port, and then your coherent receiver is able to lock on to the frequency that it cares about and ignore all the rest. So it lets you do a lot of network building in software. But there's a lot of downsides to this too. It's very power hungry. It's very expensive. These are all mini proprietary DSPs. They're very difficult to create. It's a whole field of science to go make these. And they today don't really integrate into pluggable technology. And in fact, they probably never will, because even as the DSP technology gets better and better, the pluggable technology also tends to want to shrink too. And so as much as we all hope for coherent in a QSFP28, by the time it happens, QSFP28 will be dead and we'll all be moved on to something else. So it's a lot more difficult to work with. You tend to need external transponders to work with it. So the other way that you could do this, back in the world of ASK, of amplitude shifting, is to introduce more state levels. So when I talk about NRZ, you'll typically never hear it called this, but this is also called PAM2. That stands for Pulse Amplitude Modulation with 2 levels. So again, all that is a bright or dim, a 1 or a 0. So there's a lot of work that's happening in the space of PAM4 right now. So introducing 4 levels of brightness using this same direct detect technology. So you can have lower power systems that are cheaper that integrate into pluggables. In fact, this is going to be one of the basis of 400 gig technology is very likely to need this type of technology. And today there's vendors that are shipping 100 gig DWDM tuned pluggables that use this technology. So this is what's happening here. You're introducing these four levels of state, and you're able to encode 2 bits of information per symbol change. So a little bit about how you actually engineer your optical network. So when you go out and connect fibers, even the best connectors and splices aren't perfect. So every time you take 2 fibers and you put them together, you're going to get some kind of loss. So the typical budgetary figure is 0.5 dB per connector, and it might be less than that, it might be worse than that. Depends on the quality of the connector and how well it's cleaned and particular data center. But word insertion loss is also used to describe the loss that you see from a MUX. So basically, it's the penalty that you pay just for inserting the fiber. So some real life examples, in kind of a common 40-channel DWDM AWG design MUX, you're going to see an insertion loss of about 3.5 dB. Meanwhile, if you move to an 80-channel system, a 50 gigahertz MUX, you're going to see a much higher insertion loss. You're going to see 9.5 dB. Because basically, all a 50 gigahertz MUX is 200 gigahertz MUXes at an offset plus an interleaver. So you see that add up of cost and insertion loss. Another easy way to kind of cause problems is when you have mismatched core sizes. So here you see that we had a wider core and a narrower core come together. And in fact, when you see that on an OTDR, you'll actually see all kinds of weird behaviors. If you have a misaligned core, if you have fibers that aren't perfectly mated, you'll tend to see some loss. And if you have any kind of an air gap between the fibers, the connector isn't perfectly inserted and isn't clicked in all the way, air really doesn't transmit this very well, so you'll see a ton of loss that way. And the signal will still work, you'll just see loss. So when you start doing an optical network, you need to build a budget. You need to actually look at how this is going to work. So when an optic says 10 kilometers, that is a complete guideline. I've taken 10-kilometer optics and I've made them do 25 kilometers all day and night long, but you have to know what you're doing. So that 10 kilometer is purely a guideline. It's purely a standard stated thing. The actual distance is going to depend on the quality of your fiber, the quality of your connectors, what you're doing with them. But you want to leave some margin into this too, right? You need to deal with what happens over time if someone comes along and cuts your fiber and then repairs it, and now you've introduced more loss because of the splice. Or what happens if some data center tech comes along and their grubby little hands and starts working in your cable tray and starts bending your fiber, you're gonna see some impact. And then the actual transmitters themselves cool over time. So when you buy an optic out of the box and you plug it in, you come back 10 years later, if you're still running it, it's not gonna be transmitting at the same power level that it was when it was brand new. So you need to add some budget in there to make sure that the link still works and doesn't just die randomly over time. One thing that you'll encounter in the world is different types of connectors, the PC and the UPC versus the APC. So these are different types of ferrule connectors. The physical contact or the ultra-physical contact, you'll sometimes hear it called polished contact, but it's actually physical, are the blue tipped fibers. So what's happening here is this is just a straight, the fibers align perfectly flat against each other. So in a PC standard, you're guaranteed a minus 30 dBm or dB back reflection, and an ultra physical, I'm used to saying ultra polished, but in a UPC, you're kind of guaranteed minus 55 back reflection. So less reflection that happens in this. The green tipped fibers that you'll encounter out there are what's called APC, angled physical contact. So what's happening here is you've got an 8-degree angle at the end of the ferrule, and it's getting you much lower reflection at the end of the fiber. So why do you care about that? Well, when you disconnect that fiber, even a UPC cable, once it's not plugged into something and once it's not propagating that light, it's going to cause huge amounts of reflection. It's going to cause all this power to come back at you. So if you're running a high power system and someone goes and unplugs the cable and now all that power, where's it going to go? It's going to come right back to the transmitter. It can actually damage the transmitter to have all that power come back to it. So in a high power system, you tend to see these APC systems out there. Other than that, there's really no need for it in any kind of low power system. Dispersion compensation units. So this was, remember I talked about dispersion and the opposite slope. So originally this was a big spool of fiber in a box with an opposite dispersion slope. And so at the end you run through 100 kilometers of fiber and then you might run it through another 10 kilometers of dispersion compensating fiber and re-squeeze the signal back together. And then eventually it moved to being done with Bragg gratings, and so you don't need an actual spool of fiber because the spools of fiber introduce latency and people don't like those. But historically, it added like 20% overhead. So when you had these old spool-based systems, it added a significant amount of latency to the system. But you tended to see these deployed at amp sites, and the best place to put it is in the middle of a two-stage amp with what's called mid-stage access. So you want to have your first amp take a pass at it, make the signal brighter. Then you can incur some more loss going through this, but you haven't let the signal get low. You've made it brighter before you dropped it, and then you make it brighter again when it comes out of it. And you use circulators to reduce the amount of fiber that's needed and all of that. So this was very prevalent in 10 gig technology, and you'll see it become more prevalent for things like PAM4. Actually, for things like PAM4, you need interactive, tunable dispersion compensation to make it work. So a couple different ways to deal with dispersion. Largely, we like to move to a world where we don't have to care. So if you can deal with it electronically, so much the better. So for example, when we created standards like 10G base LRM, we were able to do 300 meters of 10 gig over multi-mode fiber. That was all done by introducing electronic dispersion compensation. But dispersion is the worst for direct detect systems, and like I said, PAM4 is very finicky. So today, with the like dual 56 gigabaud channel systems that are out there, you need a tolerance of plus or minus 100 picoseconds per nanometer. So you need very, very tight, you need interactive, tunable dispersion compensation and all kinds of other properties that go into making this work. Well, coherent systems really don't care. They eat dispersion for lunch, and like I said, it actually makes the system perform better to have it. So when you build a 100 gig only system or above, you don't care. Another concept that you'll see out there is what's called the 3 Rs. So the 3 Rs are reamplifying, reshaping, and retiming. And so you move from doing one to doing both to doing all three. In reamplifying, all you're doing is making the signal brighter. You're completely unaware of what the signal was, or spacing, or brightness, or anything. You're creating another photon, right? You're making the signal be brighter. In a 2R, you're actually restoring the shape of the pulse. So you're aware that this was an electronic pulse and you've done some level of decoding, but you haven't like fully deconverted it. And in a 3R, you're actually retiming it. So not only do you restore the shape of the pulse, but you actually restore the distance between the pulses. And basically, this is what's called an OEO. So you literally go from optical to electronic to optical. So this would be the equivalent of, in a router, taking an optic, turning it into a packet, turning it back into an optic. You've completely regenerated the signal from scratch. So when you work with fiber systems and you encounter bit error rates, what happens when you encounter these impairments is the links don't just die. Like that would be nice if they just died, but they don't. What happens is they just start taking errors. They get worse and worse and worse over time. So the probability that this will happen is what's called the bit error rate. So here's some time showing you what you need to be 99% confident that a bit error rate is of a particular. So if you want to guarantee, for example, that you're only going to have 1 bit error every 10 to the negative 13, which is decent, at 100 gig, you need to test this system for 3.5 hours. At 1 gig, you need to test this for 14 days. You have to send a signal for 14 days. You have to transmit at line rate for 14 days to look to see if you're going to encounter that bit error once. So that's that. So OSNR, what's happening here is as the signal gets worse and worse and worse, the bit error rate goes up. So here's a diagram showing kind of some example comparisons of a QPSK signal, an 8 QAM system, and a 16 QAM system. And you see that the more complexity you pack into the modulation, the higher the OSNR that's required for the bit error rate to still be good. So now a quick word about the tools of the trade in working with fiber systems. So the most common thing that you'll see in the real world is something called an optical power meter or just a light meter. And all this is a little tool that measures the brightness of a signal and it displays the results. But remember that most of these light meters out there have what's called a relative loss mode. So this is when I talk about the distinction between a dB and a dBm. If you use it in the dB mode, what's happening is you're expecting to have a known transmitter on the other side, and you put it in this mode because you want to measure the loss over a piece of fiber. When you put it in dBm mode, you want to know how much light am I actually seeing. So if you tell your field tech to go out to your router and plug this in and get a reading, how much light is coming out of my optic, you need to be in dBm mode. You're seeing how much light do I actually have, not measuring loss over a pair of fiber. And literally, if I had a nickel for every time someone told me they measured something ridiculous on my fiber, I'd be a very rich man. So another thing that you see in the real world is something called an OTDR, an optical time domain reflectometer. So what's happening here is you're launching light and you're measuring the reflections that come back, and you're using that to characterize the fiber. So you're able to detect with an OTDR, you're able to figure out where the splice points are, where any breaks are, and use it to kind of characterize that the fiber is good and clean and working as expected. So here's an example of an OTDR output. And in fact, when you see these little sections where it jumps up and then jumps back down, that's a core size mismatch. So that's an example of a bad OTDR. Actually, I think that was above net in 1999. Yeah, 2000. So question people ask me all the time is, can I really blind myself by looking at the fiber? Or caution, beware of big scary lasers. So here's some words about laser safety guidelines. So lasers are broken up into 4 classes for safety. So your class 1 lasers are completely harmless, either because they're so low powered that they can't do anything to you, or because there's some way that you can't access them. So for example, your DVD player, if you still have one, probably has a powerful laser, but it's inside of a metal case that you can't get at while it's operating, so it's a class 1. A class 2 is something that's only harmful if you intentionally stare at it. So if you really wanted to hurt yourself with a laser pointer, you could do it, and you could hold your eye open, and you could shine it in your eye, but you have to actually want to do it. Because if you were doing this by accident, you would have a blink reflex and you'd be protected. So it's generally considered safe unless you're trying to hurt yourself. Class 3 is something that you can't view directly because it would cause damage to the eye and you wouldn't be protected by the blink reflex. So there's two subclassifications in there, and there was an old system and a new system, so you might see it called 3R, and it got renamed 3A and 3B. So the distinction here is your class 3As are typically your 1 to 5 milliwatt, your high-powered internet laser pointers, your things that you get from China that shouldn't really be legal. Those tend to fall in there. Anything that's in a class 3B by law should require a key and a safety interlock system, and if you have people that work around it, they all have to have goggles and protection systems and all this stuff. And then class 4 are things that burn, melt, or destroy Alderon. So when we talk about laser safety in the eye, networking lasers, everything that we're thinking about is actually occurring in the infrared spectrum. So infrared, of course, is not visible to the human eye, but there's two classifications of infrared. So there's what's called IRA, or near infrared, and that's between 700 to 1400 nanometer. And then there's IRB, or far infrared, or shortwave infrared. And that's the higher frequencies. So the laser safety levels are actually based around what can actually enter the eye and cause damage. And because the human eye didn't evolve to see infrared, your cornea actually does a really good job of filtering out IRB. So you might think that, oh, it's a high-powered laser and it's a really long-reach system, so I'm probably going to be at more risk from that, and you're actually at less risk from a medium-reach application. So the maximum power, the continuous amount of power that can be transmitted without some kind of a auto shutdown feature for a 1550 nanometer IRB type signal, if you want to be in a class 1 laser, you've got to be below 10 dBm. So typically your single channel 10 gig, 10 kilometer type optics are going to be in the 0 to 1 dBm. So every one of those is perfectly safe. To be below a 3R, or to be in a 3R, you have to be below 17 dBm. And this tends to be the maximum amount of power. Like if you were to load up all 40 channels on a WDM system, or if you were to load up a single stage EDFA, this is kind of the maximum power that you get out of there. To be below a class 3B, you've got to be below 27 dBm, which is a really, really, really powerful signal. But that's your Raman pumps, your ultra long haul type applications. And then class 4 is something that's really above that and actually causes a lot of physical damage. So in routers, essentially everything that you ever look at, if you go up to a router, even if it's a 200 kilometer reach optic, even if it's anything crazy like that, it's going to be class 1. Ironically, probably the closest thing that comes close to actually meeting the harm of the category of being outside of a class 1 and potentially able to cause damage is like a 40 gig LR4. So this is something that's centered around 1300 nanometer. It actually has 4 parallel lanes. So in a 4-lane optic centered around here, you can actually be really close to 8 milliwatts. So a 10 kilometer optic, something that you wouldn't think would be especially dangerous, is actually the worst thing that you're able to encounter on a router. Inside of an optical amplifier, they can very easily have output powers that go into 3R and 3B. And Raman amplifiers are almost always class 4. But they legally have to have auto power shutdown or reduction systems. And if they don't, they can't legally be sold. So the DWDM equipment, like probably the most dangerous thing you could ever encounter in a real data center is a signal coming out of a passive mux. So like you've taken 80 channels, you've put them all into one fiber, and you don't have any active components. You don't have an amplifier or something that actually has a power shutoff mechanism if it detects a break. So now you've started to get enough power from all these individual things put into a component that's concentrated all this light energy into one piece of fiber that can actually start to get you into 3B territory and doesn't have an auto shutdown feature. So should I be wearing goggles to the colo? Probably not. If you're playing with your standard client optics, you're in no danger whatsoever. Even on your amplified WDM systems, the light really disperses quickly once it's inside air. So unless you take the fiber and hold it right up to your eye, you're probably fine. And remember that everything above 1400 nanometers is actually mostly blocked by the human eye. So don't worry about it too much, but don't look at it with a microscope either. So why would you even look into the fiber anyways, right? If this is infrared, like you can't see any light at all. So the human eye is really designed to see between 390 to 750. So technically, no fiber, even the 850 nanometer signal that you could see. But if you've ever looked into an SR and you've seen red, there's a reason for that. Like the signal is not perfect. The generation is not perfect. So it's generating some sidebands that are falling down into the human eye visibility. One trick you can use, and depending on the camera that's out there, is digital cameras can typically see infrared. So if you take your camera and hold it up to like your remote control, you can see if you can see the infrared signal that way. But unfortunately, that's tending to go away because the nicer cameras are putting like optical filters on there to try and block this out for better photo quality. So sorry, iPhone users. As of like 4S and iPhone 5, they started putting IR filters on the camera. So people ask all the time, can optical transceivers be damaged by overpowered transmitters? And well, the answer is yes and no. So remember that most optics transmit at kind of the same power no matter what. So there's not really much variation between a 10-kilometer optic and an 80-kilometer optic. When you make an 80-kilometer optic, you're not making it stronger. What you're doing is making the receiver better. So you're able to work with a lower signal. You might have 10 dB more of sensitivity out of it. And the sensitive receiver is what's in danger of burning out. So there's 3 points that come into play here. That's what's called the saturation point and the damage point, or sorry, 2 points. So basically speaking, the only thing that's in damage is your 80-kilometer optics, your optics with very sensitive receivers. If you plug them directly into each other without any fiber in between, you can actually cross the line and cause damage. For the most part, if you're in the 40-kilometer space, what happens if you put them back to back is you just blind the laser and it doesn't work, but you don't cause any damage. And then the 10-kilometer optics don't care at all. So do I really need to be concerned about bend radius? Yeah. So you can actually, they sell tools where you want to troubleshoot and figure out what fiber you're looking at. You can stick a red light generator on the end, and you can go find the fiber, and you can bend it, and you can see the light leaking out the sides, and this is what's happening here. So even bend insensitive fibers are really just bend less sensitive. So don't go crazy like clipping them together, but for the most part, you really want to use bend insensitive fiber anytime you let your humans and your fiber come near each other. So here's kind of an example showing the different practical bend radiuses. So when you've got kind of a standard G652 cable, something that you might see designed for being in the ground, it really expects a very slow bend radius compared to much smaller bend radiuses for the cable that you can use in data centers, where you can just wrap it around a pencil and it'll still work. So a lot of time people ask, can two transceivers of different wavelengths talk to each other? Absolutely, for the most part. So all optical receivers have wideband photodetectors. So when you've got a laser receiver, it can basically see anything between 1260 and 1620. It can see everything that you would ever transmit out of a laser. You won't be able to see an 850. Those are separate systems, but like anything that's designed to work over single mode is for the most part going to be completely wideband. And coherent receivers, like I said, can even lock on to one specific signal and ignore all the rest. So lots of DWDM systems are built around this premise. So you can have a system with wavelength color 1 going one direction, wavelength color 2 going the opposite direction, and you can run this over your single strand of fiber and everything works just fine. So the only real gotcha to this is that your optical power meter needs to know what frequency you're receiving, or else it will give you a wrong power. So if you set your meter and you tell it, I'm looking at a 1310 signal, and then you send it to 1550, your power reading is just going to be off by a few dB. But other than that, it works completely. So you can also mismatch frequencies to get extra reach out of it. So consider a situation where you've got a 10-kilometer optic and a 40-kilometer optic, and an ER and an LR pair. You can probably get nearly as much distance mismatching a 1310 and a 1550 as you can with a 1550 and a 1550. Because the ER is going to transmit at 1550, which has a lower rate of attenuation, so it's going to lose less signal as it gets to the other side. And the ER is also going to have a more sensitive receiver, so it's going to be able to detect that LR signal further. So you could probably very easily get 30 kilometers out of a mismatched 10-kilometer and 40-kilometer optic just by using these properties. And so you might only need to have the optic on one side to make it work. So a lot of time people ask, do I need to clean my fiber? Yes. So an interesting thing about fiber is you've actually got a lot of mating force. You've got 45,000 pounds per square inch of pressure coming together on this tiny little ferrule. And if you've got a piece of dirt in there, it will actually embed itself in the glass. It will chip the end of your cable and it will damage and destroy it. So buy a cheap cleaning kit, go online, get them for a few bucks. It never hurts. Like if there's a piece of dust in there, it will damage a whole bunch of stuff. So you really don't want that to happen. So a bunch of other miscellaneous information about fiber. People ask me all the time, how fast does light travel in fiber? So the math here is this. So light travels at almost 300,000 kilometers per second. So your standard single mode fiber has a refractive index of 1.4679. So you do the math and you see that light propagates through fiber at about 200,000 kilometers per second. And conveniently enough, that turns out into 204 kilometers per millisecond, or 125-ish miles per millisecond. And then if you want to compare that to what you see in a ping or a trace route, you have to cut that in half again to account for round trip time. So more or less, you see about 1 millisecond of latency for every 100 kilometers or 62.5 miles of fiber in the real world. So if you ever go on Google Maps and do the distance and wonder why am I seeing such a higher value, remember that fiber never gets laid in a straight line. It usually zigzags between population centers. It gets laid in rings. There might be dispersion compensation spools. There might be all kinds of other mechanisms that are happening here. So the fiber itself is actually a much longer route than the mileage might indicate. And that's pretty much it. Questions?
Hi, Jake Kuhn, Semantic. First of all, great talk. And I've seen the previous versions, and yeah, there's a lot of great extra material put into this. I have a question about your experiences with going out and doing a deployment. And you've introduced, or you've talked about a lot of different technologies. But compared to what you can go to a carrier and what you can grab from them in terms of dark fiber or whatever, what kind of technologies did you settle upon to use based upon availability of what's out there?
Sure. So, a lot of the practical realities of how you design your fiber system depend around things like what type of technology are you trying to support. So if you're a carrier and you need to service everything from someone who wants a 1 gig or 100 meg or everything like that, and you've been in this business for 20 years and you've got a collection of customers and they're all across the map, you probably have some legacy systems and you probably have a system that is designed a certain way. And if you were to build a system that is truly new and optimized for nothing but high bandwidth and optimized for creating very efficient systems, or for very, in my case, I care about creating cheap, massive bandwidth to feed into my packet network. So I don't sell waves, I don't need to do anything like that. So I get to go out and design things in a different way. I focus on things like, how do I get more reach out of a higher modulation system? Because effectively, it's no cheaper to make a 100 gig component transceiver than to make a 200 gig. They're basically the same thing. There's no way to say, I'm going to make this only do 100 and it's going to be half the price. You're going to pay what you're going to pay for the transceiver. And the cleaner your line system, you could just double your data rate for the same amount of money. So that's what I tend to focus on, is how do you design your system for that? So lots of hybrid EDFA Raman, lots of just low noise focused design. But if you're a traditional carrier and you're out trying to support some of these older services, you might not have a network that looks anything like that. And you might still have a bunch of 10 gig waves running around, preventing you from getting those types of reaches. So.
Hi, Thomas McCarthy from Transit Wireless. I have two questions. One, in reference to CWDM and DWDM, is there one that's more robust than another in terms of, bad fiber and whatnot?
Not really. So basically, the signal itself is the same. The difference between the CWDM and DWDM is how tightly you pack them together. So you can increase robustness by changing the signal. You can send a different modulation, or you can add more effect, or you can do all kinds of things like that. But the difference in channel spacing, other than those nonlinear effects I talked about, it tends to be unrelated to that. So the smaller window you get, you might need more precisely engineered. You might need better cooling. You might need the ability to control it and make sure that it doesn't waver outside of that range. But effectively, it's the same signal. It's the same laser.
Okay. Second one, is there a training path or certification path you recommend for, I have high-level engineers know a lot about optical networking. However, I've got a lot of field techs out there that would like to learn, quite a few things that you went over here.
Good question. No, I actually have no idea. So maybe someone else does, but yeah, I've never seen that. So.
Yeah, I've seen specific training, like, how to splice fiber and whatnot, but I
Yeah.
haven't seen a broad-based one like this.
Yeah, I've never seen something like that, so that's kind of why I give this talk.
All right. Thank you, anyhow.
David Hollab, Colt Data Center Services. Great talk, Richard. I want to go back to the ROADM versus the photonic switch in the MEMS technology and assume the application is something I bet a lot of people around here do, which is sort of a metro network for rapid provisioning of, 10 and hopefully now 100 gig plus waves and circuits and so forth. And I know there's different feature sets, but when you focus on the sort of key feature sets of protection, debugging, scalability, some of these feature sets are certainly duplicated between the photonic switch and the ROADM. When you're making some of these equipment choices, what are the considerations we should be thinking about? And also, do you see GMPLS as part of the future, and how would that potentially impact those equipment choices?
So the difference between a photonic switch and a ROADM.
In add, drop, multiplexing, that kind of stuff, yeah.
Yeah, so really what you get with a ROADM is the ability to build more complex topologies and to be able to kind of steer your wavelengths around. So where it really pays off, if you're selling waves, you're selling a particular piece of light that runs through a particular piece of glass, and you define it to go exactly this, and you sell that to a customer, and you want that to be provisioned quickly, and you want that to work, and you potentially want the ability to reroute that. If all you're building is bulk capacity to yourself, it might actually be cheaper for you to just throw more bandwidth at the problem. Instead of putting in a very expensive ROADM with very expensive amps and all the latest stuff, it might, depending on the cost of the transceivers and what you're doing, it might be cheaper just to have more channels. And so if you send it to your router and you don't really care which port it lands on or something like that, it can completely change the dynamic. As for GMPLS, so having looked at the optical industry for a bit, my personal opinion is that these people are some of the worst software writers I've ever seen in my life. I mean, there's platforms out there that still run on Java and need Windows, and look like they were written by someone in DOS. I mean, just hideous stuff. So I'm not a fan or believer in any type of vendor interop being scalable and successful. A, I don't think they have the chops for it, and B, I think they're highly motivated not to have it work, because the optical vendor would much rather have you locked into their line system buying their transponders, and they'll make a pass at saying that they care, but they don't really care. So I personally am not putting much faith into GMPLS. I mean, GMPLS has been around for a long, long time. It hasn't gone anywhere, and I'm not putting much faith into any other evolutions of it actually being delivered in a truly open line system in a truly open way. It's great for press release material, but it's not really good for practical implementation.
Andrew Dole, CrowdStrike. I wanted to go back to the forward error correction part around 100 gig waves. And we, during our turnup of a couple of 100 gig waves, we came to realize that the 100 gig wave VEX standard is not really standard, and it's kind of like a bunch of different vendors have their different flavors.
Yep.
When you went through that slide, I was kind of reminded of that, maybe something to add into that deck about the different flavors, and maybe we'll get a standard someday. So the question, I guess, is do you see them coalescing around a standard, or is it, you think it's going to be this mismatch of uncompatible things at this point?
I think it's going to be a mismatch. So there are standards, they do exist, and it's a question of whether you use the standard or not, right? So there's people that do, and there's people that use different standards, and there's people that go, oh, but we made our own proprietary version, and it's just a little bit better. And of course, again, they want you to buy more of their transponders. So for the most part, I personally would never really try to take two different brands of transceivers and make them work and talk to each other. You get 98% of the benefit that you want by being able to take any vendor's transponder and and put it on your line system. That way you can just, a new vendor came out with a new technology, I can go buy that transponder. But you still kind of want same system talking to same system, or for the most part, they've all got some way to have some proprietary version of their FEC and probably other components as well. So, so not only that, but also kind of the way the DSPs work, they tend to be tuned so that they only work against themselves. And you introduce a whole different can of worms when you try to make mismatched optics in coherent world or in it's high performance stuff talk to each other. So, thanks.
Nick Guy, Knoll Communications. Thank you for such a brilliant and succinct description of some very complex things and the reason why I tell people they need to clean jumpers. My question is around dispersion shifted fiber. Do you think that it's still necessary to remove legacy dispersion shifted fiber out of kind of longer haul networks, or maybe leave it in place given the current?
Yeah, it's definitely not necessary to remove it, but you change the characteristics of what you can get. So if you were to go put in a nice new modern SMF28E Plus from Corning, you might be able to get 3,000 kilometer DP16 QAM system. And if you have some old leaf stuff in there, you might be able to only get 2,000 kilometers. And so if you need to sell something that's 2,500 kilometers, you've doubled the cost if you didn't replace that system. So it really depends what you're trying to do with it. But no, it's certainly supportable. It's just not as easy. It's not as good as if you were to put in kind of modern fiber. And personally, I'm kind of surprised more people haven't gone to putting in submarine fiber and really trying to get some high power systems out of it. But largely, I think a lot of people are kind of in the field dependent on what their vendors engineer for them. So it might be a factor of that as much as it is a factor of what could be done with the technology. Cool. That's it.